the interactive version. So as I said, this is the Python package that is primarily developed in our group at TU Berlin. It's about 10 years now. It's celebrated its 10th anniversary this year. Came out with a 1.0 stable release, but the functionality basically hasn't changed too much over the years. The goal here is to have a Python package that has all the different components to model existing systems as well as systems with high shares of renewables. That means high shares of temporally varying wind and solar, modeling of hydroelectricity. We have some systems in Europe and worldwide that have high shares of hydroelectricity, which need special modeling, and with high shares of wind and solar, also the ability to model energy storage, roughly in the way we discussed the equations last week, have to be represented. And so it's tagged here as modern energy systems or future energy systems. Basically, we want a tool that helps us understand what transition pathways towards climate neutrality are both technically feasible, economically attractive, and the ability to play through different scenarios. What happens if the electrolyzer costs are high, if the wind and solar costs are low, if the battery costs decline even further. So kind of a tool where we, given all the uncertainties in the energy system, we can play through different what-if scenarios and have some form of optimization between the different generation technologies, storage technologies, conversion technologies between different energy carriers, as well as transmission between them. So underneath, PyPSA is built with LinoPy. So the optimization problems that we talked about last year, the same framework is used in PyPSA, only that PyPSA wraps around a little bit more functionality around that. So we basically get some form of standardized optimization problem, which is built from a standardized data structure. So you have components for generators, and then with each generator, you have a certain set of constraints associated with that are typically part of generator constraints. And generator would be a power plant, for example, a wind turbine. And you have constraints like thermal limits. You have constraints like potential, how much can you build of something? Or time varying potential. So the capacity factor time series we looked at in the very first lecture. And here we have a standardized format both for the data inputs. You pass that to a module that formulates the optimization problem, communicates with the solver. So that is the part that is done by LinoPy, retrieves and processes the optimization results, again into some form of standardized output format. So that whatever optimization, electricity market or investment planning optimization you do, you have a set of standardized components, a transmission line, a storage, a generator, that have a fixed set of attributes, that have fixed set of meanings, which makes things easier to analyze systems over different scenarios. So if you want, you can look at the documentation, which we recently revamped. So if you ever want to kind of follow up on some of the functionality I'm going to show in a moment, there's a user guide, which may be worth, it will be even more detailed than what we go through now. So if there's some particular element that is interesting for you, then that's something you can go through. And there's also a set of 30, 40 examples for different types of problems. For example, electricity market problems that we're going to look at in a moment, or things like capacity expansion, which we're going to look at in the future. So basically everything we've done so far was kind of the preparation to get to this point where we're going to use PyPSA, because many of the packages that we've looked at so far are dependencies of PyPSA. So there's one or more pieces of functionality in PyPSA that use one or more of the packages that you already know. So there's all this data infrastructure for storing data about the network inputs as well as the outputs both time series and static data. It's done with pandas. There's some linear algebra calculations done with NumPy or SciPy. There's plotting done with matplotlib and cartopy. There's network calculations with NetworkX, and as I said before, optimization interfacing with LinoPy. What you need to install, basically, you can install it via pip or conda, and you already all have it in your course environments. And the basic structure is, again, very similar to many of the previous Python packages that we looked at. There's different types of components, and as components which you have kind of intuitive meaning in the context of energy systems. You have some kind of load, a generator, which is a power plant, a line, which could be a power distribution or transmission line, overhead line or a cable, a storage unit, something that can store energy. There's some nuances. There's two storage components actually in PyPSA, a storage unit and a store, which just bundles. So storage unit bundles just a few components, makes it a fixed energy to power ratio. You remember maybe that we looked at this energy to power ratio for batteries, where you had kind of a fixed relation between how much energy the storage can hold and how quickly storage could dispatch. But as with many other packages that we've looked at so far, there's kind of a container class, which is the network class. So we always talk about PyPSA networks, which is just kind of a model instance. A network has different types of components attached to them that then define the network. And this is one of the fundamental components, and the bus is another fundamental component. So a bus is not a bus in public transport. It comes from electrical engineering. You can think of it as a node in a graph, or just a region where the power plant is located, where the load is located, or just where the electrical components attach to. And almost all of these components need to be attached to some bus. So a generator would be linked to one bus, a load would be linked to one bus, a line would be linked to two buses because there's one starting bus, there's one end bus, and there's various other things, other components that you need in an electricity system. It could be that you have conversion between energy carriers. You have an electrolyzer, for example, that turns electricity to hydrogen. So a bus could also be associated with a carrier. You have one bus for electricity and one bus for hydrogen, and then you have so-called links that can connect these two buses. So that's the other component that I didn't talk about yet. You can have a link that connects to buses of different carriers, which could be electricity to hydrogen in an electrolyzer. The links, it's usually connected to two buses, but it can be connected to n buses, because there's some components in energy systems that produce more than one output from a given input. Yeah, you could have a CHP unit that from a given unit of gas would produce a certain unit of electricity and a certain unit of heat, and the electricity and heat output is somewhat linked. So links can connect two buses, two or more buses, where the flow is controllable between them, and it's not as constrained as with lines, which would implement the Kirchhoff voltage laws we talked about last week. So the line component would be just for connections between buses, between electricity buses in different regions, whereas the link more generally could tell you about transmission or transfer of energy between two or more buses. The term carrier has kind of duplicate meaning in PyPSA. It could just refer to an energy carrier. So we have buses with an energy carrier electricity. We have buses with an energy carrier hydrogen. We maybe have buses with an energy carrier heat. Or it could just refer to a technology. So components like the generator or the link, they would also have as an attribute a carrier. which could mean the technology. It could mean offshore wind or electrolyzer. So it's just a way of tracking different categories of components, where at some point you maybe have 100 different regions and you want to sum up the capacities of all electrolyzers, and then you would use the carrier basically as a column in a data frame to aggregate over that. Okay, I'll leave it at that, and the rest we'll do on the fly. But basically from that, you construct something like a graph. So it's really graph-based optimization, where all your components attach to the buses. You have some components like F1, F2, F3, could be lines, for example, that connect the different buses with one another. And then you have buses that just connect to one, and kind of the triangles here usually for demand, the kind of circles with a wave inside, usually generators, could be conventional or wind and solar. And then basically around each of the bus, you have the Kirchhoff current law, the energy balance constraints automatically for each of the individual components. You have the thermal limits. And then for the transmission lines, you have Kirchhoff voltage laws, kind of the constraints around all of the cycles in the network. So that basically means that for every component, we have a pre-assigned set of constraints where we just need to provide the coefficients of the constraints. So, for example, the capacities, the marginal cost, and things like that. Everything in PyPSA is in base of 1 megawatt, so that's the basic unit you're working with. And the design principle, yeah, as I said, is that each component is associated with a set of variables and constraints. If some component is extendable, you get some investment variables that we'll do in later today, at least theoretically, and we'll have all the dispatch variables. So all the so this problem that you see here is exactly the one I had in the lecture last week. So it's really just the thermal limits, the energy balance, Kirchhoff voltage law, the energy consistency equations. So this is just for reference. This is exactly the same what we did last time. And what's also the same that we did last time is this optimization problem. So it's also, again, a simple electricity market model, only now we're not building it directly in LinearPy. We have some components here with different fuel costs, different efficiencies, different specific emissions, so how many tons of CO2 a certain energy carrier emits. For example, 340 kilograms per megawatt hour of fuel. And the different power plant capacities in South Africa and Mozambique. You remember this example from last time, and we start off with one snapshot with a load of 42 gigawatts in South Africa and 650 megawatts in Mozambique. So let's see how we can build this in PyPSA. By convention, you would import PyPSA typically under no alias, and then we would create this empty network container object, pypsa.network. And you could, the name is basically arbitrary, but common names would be N or net or network to use that later. I find something short quite handy because you're often going to use this variable later. Okay, so usually the first thing you would add would be the buses. So kind of bus M, bus N, so something where you can later attach the components to. It makes sense to do it in that order because PyPSA will also try to validate. Your additions to the network. For example, it would warn at least if you try to add a connection between buses that don't exist. So what would we add? We would add one bus for South Africa with the n.add function. We could give these coordinates as well as a voltage level. So we could say the voltage here is 400 kilovolts. If you wonder what the units are, you can always go to the documentation, and in the user guide, you have this list of component types where you could go to the bus and you will get this table of all the different attributes that you can add here. For example, x and y as the longitude and the latitude, and also the vnom, for example. And the vnom, it says also what type this value should have, should be a floating point value, and what the unit is and what it means. So here would be the nominal voltage. And that you have for all the different components is very useful. Or it's a very common page you would look at in the documentation, what attributes exist and what the units are. So we can execute that. And then all these components, they are stored in data frames per type of component. So there would be an n.buses pandas data frame, which would have our two buses as the rows, and then the attributes that we specified, the vnom, the x and y. And then you see a lot more attributes that we didn't specify. And these are just all the other attributes of this component type, the buses, filled with defaults. So the defaults here would be that, for example, the carrier is AC for alternating current. And these are, these are just the defaults. So if you wanted to override that and specify a different carrier, you could do that when adding the component. Or in principle, you're always free to just edit this data frame like you would edit any other data frame. Yeah, that's also possible. So the method n.n, so here we added one component at a time. In principle, you can also add multiple components at the same time. And we can do that here for the carrier. So carrier is one other component class, which just keeps track of the energy carriers in the model and tracks things like a nice name, a color, or also the specific emissions of that carrier. So what you could do, so that's just one way of doing this, you could add carriers where each of the attributes, you have a list of names, coal, gas, oil, hydro, and wind, a list of emissions, so this is a dictionary that we defined at the beginning, and a list of nice names that you could use later for plotting, and a list of colors that will be used later for for plotting. And you can also always add a carrier just as a single scalar value. That's also possible. So the add function you would use actually to add all the different carriers. So we would also use it to add generators. So for example, we could add here a generator, a Mozambique Hydro, located at a bus. So this attribute here is compulsory. Could add a carrier, a pnom, so that would be PyPSA speak for nominal capacity, P for power and nom for nominal, and then the marginal cost would be maybe 0 and something like, I don't know, 20 or 30 euros per megawatt hour for nuclear or something else. You come up with that. And maybe for n.generators, it's worth just looking at another table. Here you have also this status column where you get told which of the inputs for the given components are compulsory, so which things must be provided and which things are optional. So these are the things where you can give reasonable default values. So for example, what you definitely need is you need a name and a bus, and everything else is optional. Doesn't always make sense to just add a component without any capacity, for example, but this is the kind of minimum set of attributes that you need to provide. Here you can see pnom. If you think maybe first looking at it, oh, it's cryptic, I can look at it up and say, okay, the unit here is megawatts, the default is 0, and it means nominal power for the limits on P in optimization, and P would be the dispatch variable. Okay, we can also add components in the loop, for example, iterating over the different technologies and their capacities. Add, say, add a generator with as a tag, add bus SA of carrier tag, and then we can look up in our dictionary what the corresponding efficiency for the technology is, what the capacity is, and what its marginal cost would be, and that would just be the fuel cost divided by the efficiency. And then we can look at n.generators, another data frame, to check whether our values that we added are actually the ones that we expected. So here it makes sense. Okay, we have 5 generators with correct buses assigned with them, correct pnom, and we can also just look at whether the efficiency was correctly added. So that also looks good. So next, we have the supply side, and now we add the demand side. And here we would add the load component. We have 2 loads. We could just do that separately. And the key parameter here, the key attribute is P set. So P set means it's a set power withdrawal of the load. So something that you would put here as a positive value would be consumption of power. And here we could put a scalar value. So for example, the 42 gigawatts of load in South Africa and the 650 megawatts of load in Mozambique. And then we have the 2 loads here. We can quickly check that the loads are added here. So finally, we have here a line between South Africa and Mozambique, where we have bus 0 and bus 1. So that's kind of now a component where we have two ending endpoints. And we are in Python, so we count from 0. So the first bus would be bus 0, second bus 1. SNOM would be the capacity. It's called SNOM for apparent power. So you have the active and reactive part in there, and you have the kind of impedance X, or impedance consisting of X and R. So 2 electrotechnical parameters of the line. For simplicity, I just put 1 here. Oops, let's execute that. And we can look at the line. So we have 1 entry here. The important thing that is whatever you do, your names must be unique. So I couldn't add another. So if I wanted to have a second line between South Africa and Mozambique, I should call it something like South Africa, Mozambique 2, or something completely different. It just can't be the same name. So it needs to be unique names. And we can get a sneak peek at our network with just calling n.plot, so one of the built-in plotting functions in PyPSA, where you can just see quickly how your network looks like and how the components are connected. And this is a matplotlib version, so this is just a matplotlib figure. You look at the type. Oh, actually, it's a bit more. But it's just a matplotlib figure that is shown here. And there's also an interactive version since not so long ago, n.explore, bit like in GeoPandas. It should load. I tested it earlier. If not, we can always go to the pre-built version. We don't have the patience. Yeah, so that would give you just an interactive version where you can then zoom in and also get hover information about the exact coordinates and yeah, the capacity, for example. It's a bit sad that it's not showing here, but we can work around that. Okay, basically we have now built the first PyPSA network. We have generators, loads, all connected to buses. and we have even a transmission line. And now we can kind of hand it over to LinuPy, which then hands it over to a solver of our choice. And the function for that is called n.optimize. And this function would really just build the LinuPy model, hand it to the solver, retrieve the results, and put them into these pandas data frame for n.generators and lines that I will show you in a bit. But first, let's actually solve it. So simple problem, very fast. We are using Hive here, open solver. And the results are for operational aspects. They are stored under n.generators underscore t, where underscore t would stay kind of, this is usually time-dependent data. In this case, we only have one snapshot, but to have consistency in the data structure, there's always, like if you only have one snapshot, there's a snapshot called now, and it would tell you for the different generators what their dispatch is in each of the different snapshots. In this case, we only have one row, and you would see kind of what each of the generators would dispatch. And you can work with these things like normal pandas data frames. So for example, if you're interested in kind of the percentage loading of the generators, you could just take the dispatch and divide it by the nominal capacity of the generators, and you would see kind of which generators run at capacity and which one still have capacity left. For the lines, you will see two results. You will see P0 and P1, and it just gives you so they will always have opposite signs. So kind of from perspective of bus 0, it looks like extraction of 500 megawatts. So that's where the minus comes from. And from the perspective of bus 1, the end node, so kind of the hydro goes from Mozambique to South Africa, and then in South Africa, we have 500 receiving. So P0 will tell you the flow from bus 0 to bus 1, and P1 will tell you the flow from bus 1 to bus 0. And you can also get the shadow prices here, so the dual variables of the energy balance constraints out of that with n buses T, marginal price. And you can see here clearing price in Mozambique was 0, in South Africa 172. So how does it look like under the hood? This is something you would not regularly do, but this might be a good check whether your model is built in the correct way. So the LinuPy model that n.optimize builds is stored under n.model and will become available after you run n.optimize. So it's not directly available from the start, but just once you have optimized first, or there's also a function to kind of create the model without actually solving it. And this is just the LinuPy model with the different variables under standardized names. A snapshot is the PyPSA term for time step and the name of the generators. And then you have the different upper lower bounds of the components and the bus nodal balance, so Kirchhoff current law. And you can work with that as with any LinuPy model. You can inspect the constraints like the upper limits of the generators or the nodal balance of the buses. And once you have solved the model, you can access that's actually, you can also access the objective, and later you can also access then the objective value from that. Here we already solved it, so you can actually also see the objective here. Basically you use the same syntax as for LinuPy to access everything, So also the kind of, for example, the duals of the upper limit of the generators, you could retrieve them here. So basically, kind of how much does your system cost reduce if you extend the capacity of a coal by 1 unit? And that's basically the difference between the short-term marginal generation cost and the market clearing price. So everything that is not running at capacity will show up here as 0 because you don't gain anything from building extra capacity. And for wind, for example, the marginal cost is 0 and the market clearing price was 172. So if you build one more unit of wind in this heavily simplified model, you would gain 172 reduction in system cost. Okay, so basic network plotting. Let's see. Let's hope this one renders. It's a bit odd that it's not showing. But maybe we can again go here. So what we can do, for example, we can group, in principle, we could have multiple loads in one node. So if we want to get the total load per bus, we could group by the bus of the loads and take the p-set, sum that up. So we would get a load per bus. And in the end.explore function, we could say, well, we want our buses, we want them sized by their load. We want them in orange and not transparent, and the lines should be in orchid color and should have a certain width. So we have some control over how it is presented. And that would look then like this. So here you have just the scaling, 42,000 and 650. That would represent the load. And for the supply side, we could, for example, look at the generators and think, well, this is also something that we might want to show on the buses, how much generation there is in each of the nodes. It might be different from the load because we have some transmission, so we will have some imbalance between supply and demand, not in the whole system, but between the different nodes. And we can actually plot this in pie charts because we have different types of technologies at each of the nodes. So we maybe want something like a pie chart, which tells you about the fraction of the generation of a certain technology in a node. And to prepare that, you could look at the generation and group that by bus and the carrier. So you have a multi-index series here, which tells you the generation at each bus of each carrier. And then what you maybe also want to know is what the flow in the line is. So you might want to indicate what the flows are. So you could say, for example, the end of lines P0, we want to plot as the line flow, and then the division by 5 is just the scaling so that the line isn't too wide. Let's see if that. So if I scroll down, then we would get with that code something like this, where if we zoom into South Africa, we would have a heavy amount of coal, gas, oil, and wind. We would see here in form of this arrow what the flow would be. It's shown here as it's actually minus 500, but we scaled it by 5, so it's size minus 100, and then we have the hydro generation here. So how does this magic work? In the back end, you remember for the carriers, we specified some colors. So it will automatically look up for each of the generators' carriers what this carrier's color would be. So blue for wind, for example. Okay, so modifying a network. So sometimes you will just want to, after having solved the model, you maybe want to change a few parameters. You maybe want to look at, okay, what happens if I reduce the capacity of the line? And all of these components are just pandas data frames. So we can modify and tweak values just like a pandas data frame. For example, reduce the capacity to 400 megawatts. You could see that here in the SNUM. We could re-optimize Note that I didn't specify a solver here because the default solver in PyPSA is Heis, so I don't necessarily need to do it. And what does the log to console mean? Well, it just hides some of the outputs that you would get from LinuxPy. It's just a bit shorter output. Okay, so now we get a slightly different production. The production of the Hydra is reduced by 100, and that's basically as we expected it. Okay, so we have a coal-heavy system. We have some gas capacity that is not used. So one thing that we would typically have in a system as well would be maybe, especially in future systems with planning components, we would have something like an emission limit. So somewhere where we limit the total amount of emissions of all the fossil generators. And these are the so-called global constraints in PyPSA, global constraints because they apply to the whole system that you're not modeling, and it's one of the components that is not attached to one of the buses. So the emissions of a generator, you would just calculate by taking the dispatch in units of power, which is the unit of the decision variable of PyPSA, divided by the efficiency. So you would get to a megawatt hours of fuel, and then for each of the carriers, you know how much tons emissions there are per megawatt hour of fuel. So you would get something. You would get the emissions per generator. So this is what we do here for this variable E. We take the power dispatch, calculate how much fuel would be used, and then calculate based on the CO2 emissions stored in the carriers. So we use the simple map function here. We kind of just a lookup for each of the carriers in Ender generators. What is the corresponding CO2 emissions, which is just the tons of CO2 per megawatt hour of fuel. And we would get out of that kind of the emissions per generator, or if we want to get the total sum, we would get the total emissions in this unconstrained system. And say we want to see how we can reduce the emissions of that system by 10%. We could set a global constraint, also requires a name. We could say emission limit. This is an arbitrary name. What attribute we are looking for. So in principle, it would be possible to define other attributes, could be other forms of emissions like methane leakage or something else, some other forms of greenhouse gases or some other things that you would like to limit. What the optimization sense or what the constraint sense should be. So we want to limit the emissions, but it's also fine if we're staying below that emissions. And the constant here would just be the right-hand side value of that constraint. Our emissions should be the emissions we observe in the unconstrained case times 0.9, so we have 10% reduction. We re-optimize that, and now you see that we have a bit less of coal and a bit more of gas. And that we also see in the relative loadings. Actually, we see that we're very close to maxing out the capacity of the gas. So probably further reductions of CO2 emissions are not really possible because we have a grid that is constraining the hydroflow. We have wind already running at full capacity, and oil, which has even higher capacity than the coal that is already running. So the nice thing here is that for these global constraints, we also get shadow prices. It's a constraint after all, so we can look at n.globalconstraints.mu, which would give us the shadow price of the emission limit, which has the nice interpretation that this is the CO2 price in euros per ton of CO2 that would be necessary to bring the system down to that level of emissions. It's just always a minus sign here because with that, kind of by relaxing the emissions, so by allowing a bit more emissions, your costs would reduce by that. So that's always kind of in CO2 prices, we always talk about positive values, but here it's just inverted, basically. Okay, so what happens if we now say we want to reduce emissions even further by 5%? I already hinted at that this will not be possible. And what happens in this case? Well, we get a solver message infeasible, which just means there's no set of decisions that we can make to satisfy all constraints at the same time. And in this case, in particular, the emission limit. And then we get just a warning that this model is infeasible. So better just remove the kind of reset our emission limit for later use. So far, everything we've done is kind of in memory, so in session. So if I restarted this Jupyter notebook now, we would have to re-add all the different components. And while this is kind of okay for small examples, in many cases, you want to kind of store a state of a network and solve that maybe, and then store it to file. And then for any kind of evaluation, you maybe want a different notebook and load that there. So there's also a data import and export option. There's an option for netcdf, which is the preferred data format, just because it's very efficient for large networks. But you can also import, export as an Excel file, for example, or a series of CSV files. So what I did here is there's a function export to netcdf where you can just choose the file name. It will show up here somewhere, tmp.nc. And then we can import this network under this name with this network constructor, which at the beginning we just used without any file name reference. So, so that was a small example. And now I want to load a slightly more realistic example. It's a bit outdated. It comes from a German project. It was called SciGrid. They tried to construct an open reference model of the European transmission network in kind of period 2011 to 2014 or something like that. So it's quite dated. So all the renewable capacities are not up to date anymore, but it's a kind of simple self-contained network that we often use just for testing. And it basically has I think a week of data or a day of data at an hourly resolution and a high spatial resolution. So it has each of the different grid nodes in the system based on OpenStreetMap data. It's one of the standard examples in PyPSA. It's an example module that you can just load a few pre-built networks, which we'll just call N2 here. And we'll also do a few tweaks to that model. For example, we say that the line loading of the transmission lines, it can only go to 70%. It's kind of more conservative conservative estimate that kind of you wouldn't get any overloadings if any one of the transmission lines fails. It's more realistic how transmission systems are operated nowadays, and there are 3 known mistakes in the data. So we're just kind of tweaking some of the capacities of 3 of the lines. So now the major thing that is different is that we have some form of time resolution. And there, the question is, how does PyPSA keep track of the so-called snapshots, the time steps of the model? And this is done under n.snapshots. And here I'll just show the first 4 snapshots. In this case, it's a date time index that refers to kind of different hours on the 1st of January 2011. But it could also be just, it doesn't have to be a date time index. And now we have also inputs such as load time series that vary over time. So we have also inputs that are stored under loads underscore t, so the dynamic attributes, but they're also still called pset. And here I'll just show the first 3 entries of columns and rows. We basically have kind of snapshots as an index and the loads as the columns. So if you want to get a quick overview, you can just use this series, sum up along all the axes, and then plot it to get a feeling for kind of what the total load in the system is. So you have kind of some daily variation here. The same you can do for capacity factor time series, because you have some renewables there where your capacity factors change over time. And the PyPSA term for capacity factors is called Pmax per unit, Pmax PU. So it means the maximum P, the maximum dispatch in units of power, or in units per unit. This is just relative to the nominal capacity. So it's just really the same concept as the capacity factor. You have values of between 0 and 1 here that are multiplied with the rated capacity of each of the generator. That was the pnorm attribute. And here, so let's look at that briefly. We have here the different sorry, I should have done that here. So we have the kind of time steps as the index and the different generators as the columns. And we can just group by all the carriers and do the mean. So we get the mean capacity factor per technology. And here you can see in blue how you have, I mean, it's the 1st of January, so the capacity factors will not be super high for the solar, but you get this kind of daily profile here, kind of slightly lower wind towards the evening. Again, this is just to show that you can work with these things just like normal pandas data frames. You can also do the same for the generator capacities. So we can take all the generators, group them by capacity, and look at the pnorm, the nominal value, sum that all up, and we would get just an idea of what the gigawatt capacity would be per energy carrier in the system. And that already shows you that kind of your wind onshore, wind solar are quite far kind of below what we have in the system today. And there's also still a fair amount of nuclear in the German system here. Okay, but interesting bit here now would be that we not only have a time resolution, but we also have a high spatial resolution, and we can use the explore function for that again. So what I'm going to do here is I have I'll sum up the load of all of the different snapshots. I can simply sum up the load here to get a load in megawatt hours because I have hourly resolution. Yeah, so I have a megawatt value for each of the hours, so that gives me a value in megawatt hours. Sometimes your models might be resolved for every second hour. So you have 2 hourly resolution or 3 hourly resolution. In this case, to convert from the power to energy, you would have to take into account the weighting of the snapshots of the time steps, how long they are. And for that, we can also use n.explorer, which probably is not loading again, but that's no problem, or just a small problem. So which would just give us a map like this. So now it's actually a bit more useful than in the previous example that we can actually zoom in to different regions. You could zoom in to Potsdam, Berlin. You can see, well, I should adjust the scaling here. Then it maybe looks nicer if I want to zoom into a particular area. But we get a gist of kind of where the major loads are in the network. You have a lot of clustering here in the Ruhr Valley. And you even have kind of the network here is obviously cut off. So the interconnections to Denmark are shown, but nothing else of the Danish system. Okay, next. we maybe want to show also the supply side, not only the load. And again, we can do the same as we did before, that we group by bus and carrier and plot the nominal capacity. So we have again a multi-index Panda series with a bus as the first index, carrier as the second index. And we have, or we need to define, because it's not done directly in the network, we should assign some colors to all the different energy carriers. And then we just add these carriers to the network, the keys as names and the color as colors. And then we can also say the bus sizes should be scaled to these capacities. And as they are now multi-indexed, we will get a map like this, where just the colors are automatically looked up. And you can see here, you can see kind of the brown code here around Duisburg, also in Lausitz, and yeah, all the other things basically. Yeah. We can solve this as a market optimization, which will take into account the capacities in each of the nodes, take into account the renewables, availability, the time series of the load, and there are even some storage components in there. There's some pumped hydro storage, so there could even be some arbitrage between kind of pumping up water in one period and pumping down water and generating electricity in the other. So we can optimize that. There are a few warnings. It's always good to look at that. Sometimes you can also ignore it. So that takes now a little bit longer because we have a couple more nodes here, but still it's a fairly simple problem. We get kind of an objective out of that. And now we can add also information about the line loading, for example. So line loading would just be kind of the absolute value of the flow. So we don't really care about the direction of the flow. We just care about the absolute value. And then we would divide it by the nominal capacity. Because we restricted the line loading to 70% of its actually loading, we maybe want to show it as kind of fully loaded if it reaches the 70% of the nominal loading. So we just also multiply it by the S max per unit, so the per unit availability factor on the capacity. And then what we can do, we can use n.explore. The bus sizes we don't worry about. We just set one value here. We want the coloring by the absolute line loading. Or actually, it's already absolute, so we don't actually need this. We can indicate the flow with the arrows by just kind of taking P0 and scaling that to some extent. We can choose what color map the coloring should use. And then maybe we could also, another dimension we can size is that the line width should be proportional to the nominal capacity, so that kind of high capacity lines show up as wider lines. So when we execute that, we would get an image like that, where we could directly see kind of where there are congestions in the network. So the more yellow the colors here are, the more loaded the lines are. For example, you have here some heavy line loading here between kind of on this east-west connection between Magdeburg. You have a bottleneck. You have a bottleneck here, and then yeah, and everything that's blue is basically not heavily loaded. So there's a lot to explore. You can spend a lot of time zooming in and out. But if we continue, it's maybe sometimes also a good idea to get a rough overview of the total system. So maybe we want to look at the overall energy balance of the system across the time domain. So we looked at similar charts like that before, like the from energy charts. And we maybe want to see kind of how does the dispatch of the different components evolve over time. You can see here kind of the solar in yellow coming in throughout the day. We have some kind of the gray part here is the load, but we have some extra load here where the pumped hydro is charging, which is then discharging up here. And then we have wind and what else? Yeah, nuclear. What is there? Some nuclear here. Yeah, so the pink one is here's the nuclear. You can toggle on and off a few things, and the base unit here is again megawatts. Good. So this is what you get interactively, but you can also get that as a table and do your own things by just looking at the energy balance, and this would give you just kind of the total sum of the system, the total energy mix, and if we want more digestible units, maybe in terawatt hours, then we can also. No, that's not correct. It's just so it's just the day. So maybe in gigawatt hours, then we can get the energy balance where just the negative values are the consumption, the positive values are the production. And you can see here this consumption of the pumped hydro. This is just the conversion losses by pumping up water and pumping down water. And this is the losses in conversion. Good. What else? Oh, that was actually what I wanted to do afterwards. So this, I already used it. So there's a statistics module, which gives you just basic statistics, basic metrics of the systems you have optimized. So among other things, the energy balance. So this is the one we just looked at, just rounded and sorted from lowest to highest value. But also the operational costs. So the kind of basically the objective just split by the different components. So you can see for which components you have or which carriers have the highest cost here. And in kind of future systems, you would then also have a CapEx component where you can see how costly was it to invest into the systems. There's a curtailment function which gives you how much energy had to be curtailed. There's also a revenue function which tells you about the profits of the just the revenues of the generators, just the dispatch times the market clearing price. So there's a few more statistics to explore, and I hope these are kind of listed in the documentation as well. So kind of there's a longer list of statistics that you can directly access without having to do calculations on the component data yourself. Okay, good. So what have we done? So we've solved our first PyPSA problem. We've kind of reproduced the LinearPy examples from before. We've learned basics of accessing the results, building small interactive plots to explore the networks, both the input data as well as the output data. And then we briefly looked at the statistics function to quickly access aggregate results. It doesn't give you component level results. So for example, if you wanted to look at the dispatch of individual generators, you could always call it N2. So this is what we did originally. You could always just look at the raw data where you can see the dispatch of every individual generator should you need it, and then you can make regional aggregations and so on. So I would leave it at that. What comes next time is how we can use PyPSA for capacity expansion problems, so future-oriented problems. But for that, we have to do a short lecture later this afternoon to introduce that from a theoretical point of view. And I would say we take maybe a 20-minute break and then continue after that.